Thank you for joining me. So this is 3.4, zeros of polynomial functions, which involves tons of definitions and theorems and shows you basically everything you can do with a function and how to analyze every aspect of a polynomial. So there's a lot going on in this section, and it's important to keep track of all the vocabulary so that you know what's going on. So 3.4 covers using the fundamental theorem of algebra to determine numbers of zeros of polynomial functions, finding rational zeros of polynomial functions, finding complex zeros using conjugate pairs, finding zeros of polynomials by factoring, using Descartes' rule signs and the upper and lower bound rules to find zeros of polynomials, and finding zeros of polynomials in real-life applications. So there's tons of stuff going on here. The bulk of the assignment for this week relies on this section. So I'm going to start with the fundamental theorem of algebra. So it says that if you have a polynomial of degree n, as long as n is greater than 0, which is normal for polynomials, then your function has at least one zero. Basically, as long as you have a polynomial, it will have at least one zero. Now it specifies it's in the complex number system because there could be imaginary zeros. So when you graph it, you may not see any x-intercepts because they are imaginary, they're complex numbers. So every polynomial is guaranteed to have at least one zero, but it may not be an x-intercept. It's just a zero. So this is where we talk about the difference between zeros and x-intercepts. So we've got a couple more definitions. We have the linear factorization theorem. So this is saying if you have something of degree n, then you can factor that into n different factors, but some of them might be complex numbers. So if I have a cubic, I can factor that into 3 different factors, although some of them might have complex numbers and imaginary numbers in them. So they may not all factor nicely, and there may be nasty decimals or square roots, but every polynomial can be factored, and your degree tells you how many factors you have. So that is basically what the linear factorization theorem says. And then the factors of the polynomial definition here says that you can write something as a product of linear factors or quadratic factors. And the quadratic factors are used if you would have like complex zeros if you factored that quadratic. So that's just sort of a sidebar that says when you get complex numbers that show up, you can leave it in a quadratic form. Next is the rational zero test or the rational zero theorem. So this has different names depending on which textbook you use. Our textbook calls it the rational zero test. I have seen it in most textbooks called the rational zero theorem. So that is basically the same thing. So this is basically telling you how to find out what it could factor into, basically. Because if you have a polynomial, if you have a quadratic, you can just factor to use the quadratic formula. If you have something larger, there's no starting point. There's no easy way to determine how to factor that. So you have to basically guess and check. And so the rational zero theorem is giving us a list of numbers to check so that you're not picking out of a million numbers, but you actually have a set of numbers to choose from. So instead of like having infinite possibilities, I might have 20 possibilities. It narrows it down. So it basically says, so we've got our polynomial here, and we care about the coefficient of the leading term and then the constant. So then this only works if there's integer coefficients. So it has the form of p over q. So p comes from the constant term, q comes from the leading coefficient. So your zeros are formed off of the factors of those two numbers. All the choices that can factor into each of those, and then all of the combinations of that. So this makes much more sense when you see it in practice as an example. So list all the possible zeros of f of x equals 8x fourth minus 26x cubed minus 27x squared plus 11x plus 4. So to do this, we need to use the rational zero theorem or rational zero test. So I'm going to just write that down. So I need to identify my P and my Q. So P and Q are the first and the last numbers. So my factors of P. So the factors are all the numbers that divide. This is terrible F. Let me try that again. All the numbers that divide evenly into P. So P is 4. So all the numbers that divide evenly into 4 are 1, 2, and 4. Then we look at the factors of Q. So Q is 8, so all the numbers that divide evenly into 8 are 1, 2, 4, and 8. So you have to write down all the numbers that go into it. Then our rational zero theorem says our possible rational zeros are plus or minus P over Q. So you're taking those factors of P, you're taking the factors of Q, and then you can either have a positive version or a negative version of it, and those are all of your choices. So one way to do this is to make a table so that you can be sure that you've tried all of the combinations. So let's say I have my factors of, so I want to have P over Q here. So I have my factors of P going across, 1, 2, and 4. And then my factors of Q going down, 1, 2, 4, and 8. So I'm going to just make a table. I should have put this a little bit higher up, but that's okay. And so our factors are plus or minus P over Q. So I have plus or minus 1 over 1, which is just 1. So I can just write that as 1. Then moving to the right, I have a P of 2, Q of 1. So that's plus or minus 2 over 1, which is 2. And then moving to the right, 4 over 1 is plus or minus 4. Then I do the next row. P over Q, I have 1 over 2, so that's plus or minus 1/2. Then I have plus or minus, and then I have 2 as P, 2 as Q. 2 over 2 is 1, so I have 1 once again. And then 4 over 2 is 2. And then I have plus or minus 1/4, so 1 over 4. Plus or minus 2 over 4, which reduces to 1/2. Then 4 over 4 is 1. Then I have plus or minus 1 over 8. Plus or minus 2 over 8 reduces to 1/4. And then plus or minus 4 over 8 reduces to 1/2. So I'm taking all of the combination of the factors of P, all of the combination of the factors of Q, and I'm doing P over Q. So now you've got all of the choices, but some of them are repeating. So you only write down each one once. So going maybe say straight across, I have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2, then 1 and 2 repeat again, plus or minus 1/4, then I have repeats, and plus or minus 1/8, and then I repeat. So those are all the possible zeros. So if you're factoring, those are all the ones you're going to try when you factor. You're going to factor by making guesses of like x minus 1, x plus 1, x minus 2, x plus 2, x minus 4, x plus 4. And you're going to use synthetic division to do that. So the rational zero theorem is giving you a starting point when you have to factor something that's larger than a quadratic, because we don't have a shortcut like the quadratic formula. So the only way to do it is by guessing and checking. and having some possibilities. This is basically what a computer does, is because it's very, you have numbers that you can check, you have a list of possibilities. If you have some sort of computer that can factor things for you, it is going through all of these possibilities until it finds some that work. So this is the only way to factor things that are larger than a degree 2. So you have to use the rational zero theorem to at least narrow down your choices and give you a starting point. Are there any questions on the rational zero theorem or the rational zero test?
So do you plug in the 1, the 2, the 4, the 1/2 as a into the x, and then work it from there, or
yeah.
Okay.
Yeah, so what you would do is you can plug it in for x, and then if you got 0 out once you evaluate it, that tells you it's a 0. So
okay.
Instead of just trying random numbers, you at least have a list of some that work. But yeah, you would have to plug them in, or if you did synthetic division, you could use synthetic division to find out if it gets 0 at the very end of the synthetic division. But that's the only way then to see if they're zeros. These are just possible. They may not be zeros at all.
All right, so this is a shortcut to I guess taking a guess at it. Right?
Yes. Instead of just guessing and just not knowing where to start, you have some choices.
Awesome. Okay.
Yeah. Now the downside of this is that if your polynomial is made entirely up of complex zeros, like they're all imaginary, this won't work because none of these numbers will work. So this only works if at least one of the zeros is a real number. So if none of these possibilities work, that tells you they're all complex numbers, and then you're kind of screwed in a way. But we're not going to deal with any of those, so you don't have to worry about that. So speaking of complex zeros, if you have complex zeros, they occur in conjugate pairs. So conjugate pairs, that is where you have like 1 plus I, and then its pair would be 1 minus I. So if one of those is a 0, then the other one is also a 0, where it's the same real number, but it has the opposite sign for the I. So complex numbers always occur in pairs. So if you have something that's a cubic and one of them is complex and the other has to be complex, and then you have 1 0 left over. So this is helpful because it can kind of, like, if you figure out one of them is complex, then you have fewer zeros to find because you automatically know the second one, because they're just the same, just opposite signs of the I. So they always come in pairs. So here's an example. Find a polynomial function of least degree having only real coefficients and zeros of x or zeros of -4 and 3 minus I. So on the, let's see, I know for sure on the final there's a question like this. The quiz in week 6, there's a question like this where you were given the zeros and then you have to write what the equation looks like. So this is how you do that. You find your zeros and then you write the equation. And we actually do have to do that on the assignment as well, because you're factoring it using synthetic division, and you find your zeros and then you have to turn that into how it's written factored. So how this works, so if we have a 0 of x, or of 0 of -4, you write x equals -4. Then we have a 0 of 3 minus I, so I have x equals 3 minus I. And then because these come in conjugate pairs, your third 0 is going to be 3 plus I. So this is going to give us a cubic when we are all said and done, because we have 3 different zeros here. So we need to first write it in factored form. And the way to do that is to take each of these 3 equations and set the right side equal to 0. So if I take the first one and I add 4 to both sides, I get x plus 4 equals 0. For the next one, I'd have x minus 3 plus I equal to 0. So I had to subtract the 3 and then add the I. And then I get x minus 3 minus I equal to 0. Now, so working the factoring process backwards and the solving process when you factor. So when you factor something and solve, you factor it, then you set each factor equal to 0 and solve for x. So we are doing that backwards. So once you set you got your zeros, you then solve that so that one side's 0, and then those are your factors. So we would have f of x equals x plus 4, x minus 3 plus I, and x minus 3 minus I. So you can see that the zeros are basically the opposite sign when you turn it into the factored form. Now we want to multiply all this out so that we have it, as a single polynomial. And the best thing to do is to do the imaginary stuff first, to multiply that out, because that will save you some time and grief later on. So I'm going to use the table method for this because I have basically 3 things that I am multiplying. And so when I do this, I make a table because that way I know that I have multiplied everything together. So I have x times x, which is x squared. And then I go across. X times negative 3 is negative 3x. X times I is xi. Then second row, negative 3 times x is negative 3x. Negative 3 times negative 3 is 9. Negative 3 times I is negative 3i. Then I have negative I times x, so that's negative ix. Negative I times negative 3 is a positive 3i. Negative I times negative I is a negative I squared. So most of these things cancel out. So for example, the xi and the negative ix, those add up to 0. And then the negative 3i and the 3i, those add up to 0. So now I have x plus 4, and then when this multiplied out, I have x squared. I add my x terms, negative 3x minus 3x is minus 6x. And then I have a 9 and negative I squared. So I squared is negative 1, so negative I squared is positive 1, so that's 9 plus 1, so that's going to give me plus 10. So now I need to multiply once again to get the full polynomial. So I'm going to, again, I like to set up a table with this. So I have x squared minus 6x and 10, and then I have x and 4. And I just do this so I don't have to get lost in what I'm multiplying. So the first row, first column, x times x is x cubed. Then I have x times negative 6x, which is negative 6x squared. Then x times 10 is 10x. Then second row, 4 times x is 4x squared. 4 times negative 6x is negative 24x. 4 times 10 is 40. And then I add all of my like terms there to get my final answer. So I'm going to start with f of x equals, I have x cubed. My x squared terms, I have 4 plus negative 6x, so that's negative 2x squared. Then I have negative 24x plus 10x, so that's negative 12x, and then plus 40. And so we basically worked the whole factoring process backwards. So we started with the zeros, rewrote them, put it in factored form, and then multiplied it everything out. So do you have any questions?
Where did the negative I squared go?
So the negative I squared, that is equal to, let me get a different color here. So negative I squared is negative, and then I squared is negative 1.
So positive 1.
So that gives me positive 1, and that's how I got the 10. 9 plus 1.
Gotcha.
Mm-hmm. Any other questions? All right. All right, so now the next rule or theorem we're looking at is Descartes' rule of signs. So this is also something that you need to do on the assignment. And this is another way to kind of help narrow down our guesses when we're trying to factor. So it is used to basically figure out how many zeros are positive and how many are negative. And so you can use it to determine if you should be trying positive numbers or negative numbers. Because our rational zero theorem has plus or minus. You can have a positive or a negative. And then using Descartes' rules of signs will tell you when you should stop checking positives or stop checking negatives, essentially. So the number of positive zeros is either equal to the number of variations in sign of f or x, or less than that number by an even integer. What that means is you subtract 2. So if you have the sign changes 4 times in your coefficients, we look at the coefficients here, then you can have 4 positive zeros, or 2 positive zeros, or 0 positive zeros. So it could be that you have all 4 of them are positive, 2 of them are positive, or none of them are positive. And that's based off of how many times the coefficient changes from positive and negative or negative to positive. Then to figure out how many are negative, you have to first plug in negative x, which is going to switch all the signs on the odd powers. Switch signs odd powers. And then you do the same thing. You count how many times the coefficients change from a positive, negative, or negative to positive, and then you subtract 2. So if it's an even number, you just keep subtracting 2. Like if it's 6, you can have 6, you can have 4, you can have 2, you can have 0. If it's an odd number, you can't get to a negative. So let's say you ended up with 3 sign changes. Then you could have 3 or 2 or 1, but you can't go to -1 because you can't have -1 zeros. So it doesn't tell you exactly how many are positive or exactly how many are negative, but it gives you an idea so that you can use that information to determine whether if you know that you can have only an even number of positive zeros and you already have an even number of zeros, then you might want to stop checking even number of zeros. You already have let me rephrase this. Let's say you use this rule and you determine that you can only have an even number of positive zeros. So once you get an even number of positive zeros, you might want to stop checking the positives and start checking the negatives. So that's how you could use that. So here's an example of how this works. Determine the different possibilities for the numbers of positive, negative, and non-real complex zeros, because this can also tell you if you're going to have any imaginary zeros. So we have f of x equals 2x to the 4th plus 3x cubed minus 5x plus 4x plus 1. So first we're going to check the positive zeros by checking how many times we're changing sign. And we're just looking at the coefficients. So I'm going to just write the coefficients here. And so we change sign from a 3 to a -5, from -5 to 4, and then from 4 to -1. So that means there are 3 sign changes. So I could have 3 positive zeros or 1 positive zero, because we always subtract 2. So we could have 3 or 1 positive zeros based off of how many times that changed sign. And then we look at the negative zeros. Oh, my dog is barking. I think she got stuck in a corner. I'll be right back. I'm going to just check on her. Okay, she got stuck behind the door. She was, like, the door was open and she got stuck between the wall and the door and then couldn't figure out how to get back out. Okay, so negative zeros. What this means is, again, we're looking at the coefficients, but we're looking at what happens when we plug in negative x. And when you have a negative x plugged in, anything with an odd power will switch signs. So f of negative x would be 2x to the fourth minus 3x cubed, then minus x squared, then minus 4x, then minus 1. And this is because if you plug a negative into something cubed, you get a negative out. If you plug a negative into something with an even power, it becomes positive out, so it doesn't change anything. But if you have an odd power, it will switch the sign. So looking at the coefficients, we have 2, negative 3, negative 5, negative 4, and negative 1. So we only change signs once, from 2 to negative 3, and then we stay negative. So that means we could have 1 negative 0. So then if you think, okay, well, how many non-real zeros can we have? How many complex number zeros? So this, we have to look at, our degree is 4, so that means we should have 4 zeros. So if let's see, I'm going to just write positive, negative, and then I'm going to put I here. So I could have 3 positive or 1 positive. I could have 1 negative, and then I have to look at what's left over. So 3 plus 1 is 4, so then that would mean 0 of them are imaginary. Or if I have 1 positive, 1 negative, then to get up to 4 I need 2 more, so that the other 2 could be imaginary. So looking at it that way, then you could have 2 or 0 non-real complex zeros. It just means that you may get some imaginary numbers. So they have to add up to 4 when you're looking at the combinations here. Are there any questions?
I think I'm going to have to talk off with you on that one.
Okay. That's fine. Okay. Well, I'll be doing another example later when I go through an example similar to the assignment. So hopefully that one will help.
Okay.
Okay, next we have the upper and lower bound rules. So this is taking a look at when you do synthetic division and determining if you found the highest possible zero or not, or the lowest possible zero or not. So let's say you're dividing using synthetic division, and the number that you're using is positive, and then each number in the last row is either positive or 0, then that is the highest. It basically means there is no 0 higher than that. So an example of what this would look like. So the way I set up my synthetic division, let's just say A, B, C, and D, and then I have just these numbers underneath. So it is talking about these numbers that you got from the synthetic division. So if you are trying to find a 0, and all of those are either positive or 0, and you are using a positive number, then that means there's no 0 that's bigger than what you just tried. So let's say we had our list and we had zeros up to 8 possible. We had like plus or minus 1, 2, 4, and 8. If I had 2, it did my synthetic division, and everything was positive or 0, that means I don't need to check 4 and 8 because there's not one bigger than that. So it can also, this is another theorem to help you, or a rule to help you narrow down your choices. If C is negative and they alternate sign, and zeros can count as either sign, then that says that there's no zero that's smaller than that one. So if I was trying -2 and the alternated sign, then I don't need to check -4 and -8 because there's not going to be anything smaller. So this is just another way to narrow your choices when you're trying to factor. And now I'm going to work through an example that is similar to the assignment. I'm going to go through all of the steps in the assignment, but just with a different polynomial. So it's not the same function, but all the steps are going to be the same. So the first step is to find the degree of the polynomial, and the degree is equal to the highest exponent. So since the highest exponent here is 4, this is, oops, I'm in the highlighter. Let me actually get to the pen. This is degree 4. Now the maximum number of turning points, that's something that was covered in 3.2. It's always 1 less than the degree. It is n-1. So that means I'm going to have 3 possible turning points. There may be less than that, but that's the maximum that we could have. Maximum times it would change direction, basically. Then how many zeros does it have? So this is the fundamental theorem of algebra, essentially. It's the same number as the degree. So there will be 4 zeros. Some of them, it's possible to have repeated zeros. So you may have 3 different numbers, but because one of them is repeated, it still counts as having 4. Next is the leading coefficient test to describe or draw the left hand and right hand, or right end behavior. That should have said hand. The typo in the assignment, but you get the idea. So I prefer to draw this. And this leading coefficient test is talked about in 3.2. So our leading coefficient is 3, and we have a 3x to the 4th as our leading term. So the x to the 4th in even degree means that we're going to be sort of looking like a parabola, and it's either going to be an up or a down. Because the coefficient is positive, it's going to be up. So our end behavior looks like a parabola. There may be other stuff going in between, so it could be squiggles like that, but the left and right end, those are going up. So that is the end behavior. So you can draw it sort of saying like we've got 2 sides going up and down because we've got a positive coefficient and it is even, so it opens, it's going to look like a parabola. So that comes from 3.2. So now we have an idea of what this is going to look like, and we know how many zeros we're going to have. Next step is to figure out what our possible zeros are. So this is the rational zero theorem. And now this problem that I chose is a little bit tricky because there is no p term, because there's no constant. So we have to first factor out an x. So because there's an x in every term, so I can factor that out. That gives me 3x cubed minus 11x squared plus 8x squared plus 4. And now I'm going to use the rational zero theorem with that part, with the x cubed part. And by factoring out that x, I've already determined that one of the zeros is x equals 0, because I already factored it just by looking at it. So the 4, that is p, the 3 is q. So our factors of p are 1, 2, and 4. Factors of q are 1 and 3. And so now we're looking at plus or minus p over q as our possible zeros. So I don't have room to make my little table here. I should have given this a whole slide. I did not. So if my factors of p are 1 and then my q are 1 and 3, I get plus or minus 1 or plus or minus 1 over 3, 1/3. If I have the p is 2, I get 2 over 1, so that's plus or minus 2 or 2 over 3. And then if I have a p of 4, that's 4 over 1 or plus or minus 4 over 3. So the possible zeros are 1, 1/3, 2, 2/3, 4, and 4/3, and you could also have the negative versions of those. Next is Descartes' rule of signs to determine the possible numbers of positive and negative real zeros. We're not going to worry about the imaginary zeros. We're just going to worry about how many we might have that are positive and how many that are negative. And you know what? I'm going to move all this into I'm going to briefly stop sharing and just make a new slide so that I have more space. Because now that I'm looking at this, I did not give myself enough space. So just bear with me while I temporarily stop sharing so I can duplicate, and then make a new slide. Okay. And then I'm going to go back and share. Okay. So this way I'm going to rewrite this so that you can actually, I'm going to make my little table. Oh, where did I put my, oh, there it is. Where did I put my stylus? Okay, so I'm going to rewrite, oh, it won't let me rewrite this. Okay, so I'm going to make my table now, my P over Q table. So that P is 1, 2, and 4, and then Q is 1 and 3. So that way you can see where these possible factors are coming from. So I have plus or minus 1 over 1, plus or minus 2 over 1, which is 2, and plus or minus 4 over 1, which is 4. And then we have plus or minus 1 over 3, so it's 1/3, plus or minus 2/3, and plus or minus 4/3. So just make my table a little thicker there. So we have 6 possible numbers for zeros of either sign. And so when we start getting to the factoring part, I always try to pick the whole numbers first because they're just a lot easier with the synthetic division than trying to do fractions. Okay, so now Descartes' rule of signs. So far we have factored this already. We factored out an x, which left us with 3x cubed minus 11x squared plus 8x plus 4. So I'm just going to keep that there so that we remember that. But Descartes' rule of signs we can do based off of the whole polynomial here. So the number of positive zeros possible. We look at the coefficients. So we have 3, negative 11, 8, and 4. So when I look at when we change signs, we go from a positive to a negative, and we have 3 and then negative 11, and then negative 11 to 8 is another sign change. So we have 2 sign changes. So that could be 2 or 0 positive zeros. I'm going to just leave that there. Now let's look at the negatives. So we have 3x to the 4th. When I plug in a negative x into something cubed, the coefficient will change sign. So now that's plus 11x cubed. Then even coefficients, or even exponents, the coefficient stays the same. Odd changes, so that 4x, if I plugged in a negative x, that would become negative 4x. So now my coefficients are 3, 11, 8, a -4. So I'm positive, don't change anything until I get to 8, and then I change to a negative. So there is one sign change. So I can make a table here, and because we just want to know the number of positive or negative zeros. So I could have 2 positive zeros and 1 negative 0. Because that was what I got here from the sign changes. And then I need to, if it's even, or well, if it's odd, or you need to subtract 2. So the positive, I had 2 sign changes. That could also mean I could have 0 positive zeros. And if I subtract 2 from 1, I still get a negative. So then I still have only 1 negative 0. So this is telling me that I could either, when we factor, we could have 2 positive zeros, or we could have none of them that's positive. And it's telling us that basically we are going to have 1 negative 0 because there was 1 for both of those. So this is guaranteeing us that at least one of the zeros is negative because I got 1. So if I want to guess and check, I would say, okay, I know I have at least 1 negative, so I better start checking the negatives when I start factoring. And then as soon as I get a negative 0, then I can stop checking negatives, and then I can move on to the positives. So that's how Descartes' rule signs works. Does that help a little bit further from the first example that I did?
The light bulb's starting to flicker a little bit.
Okay, you might have to see several examples. Yeah, this one's always, this is probably the, yeah, this rule is the hardest rule for most people to get. And I think it's just a matter of seeing several different examples of how it works. Okay.
So.
Yeah, go ahead. I'll go back to my slide.
Do you mind if I ask a quick question? So,
no, of course not.
Because it went 2 places, right? That's where that rule of 2 comes in, the 2 sign changes. So you moved the negative 11 became the negative 4 in that.
So, okay, so the 2 signs, just how many times did it change, like alternate signs? So we went from positive to negative, and then we went from negative to positive, and then we stayed positive, so that didn't change sign. So that, go ahead.
In the first example. For
so
what we started with.
The one all the way back?
No, just the one given the following polynomial. No, I was talking about the one we were working, just barely.
Okay, yeah, okay. Re-ask your question. I might have misunderstood.
Sorry. So
okay.
If you plug a negative into that, it changes the signs all the way throughout. And it was just a little confusing that it switched 2 places and some stayed negative. And
when you plug in a negative, it only changes the signs for the odds. So, like, let me actually try by plugging in -1 so you can see this. 3 times -1 to the 4th plus 11 times -1 cubed plus 8 times -1 squared minus 4 times -1. So -1 to the 4th power is a positive 1. So that would be 3 times 1, which is still 3. So that one doesn't change sign. -1 cubed is -1 times -1 times -1. You will end up with a negative out. So that would be 11 times -1, which is then how, oops, I should go back from my original. That's supposed to be a minus. I switched too many. I looked at the one after I changed the signs already instead of the original. So the original had -11. So that -11 with the -1, that's how that became a positive 11. Then we had a plus 8x squared and a -1 squared, that's a positive 1. So that's 8 times 1, so that stays at 8. And then we had plus 4x, and when you plug in a negative, that's 4 times a -1, that becomes -4. So that's why that switched to -4. Does that help?
It's getting there.
Okay.
It's just really confusing.
I think a part of it is I'm not showing the step where I'm plugging in a negative because I know the rules, that if you plug in a negative with an odd power, it's negative out, so it's going to have to switch the sign. I think that's what might possibly be missing here.
Okay.
So if you don't want to try to figure it out, you can just tell yourself odd power changes signs when I'm doing the Descartes rule signs for the negatives, and you could just say that's the rule. That's what I'm going to follow. Any other questions?
Let's try mine.
Okay. All right, so the next one is use the previous information and synthetic division to factor the polynomial. So this is where we're going to try to find the zeros using synthetic division. And we're going to use all of this information. So I'm going to set up my synthetic division. And actually, because I already factored an x out, so we already know one of the zeros. We're going to use the cubic version because we've already factored one step. Okay, so we know that at least one of the zeros is negative because that came from Descartes' rule signs. So we need to go to our rational zero theorem, and we want to try negatives. So I would try the whole number. So I would try -1, -2, -4, and then start trying the fractions because I tried out the whole numbers first. So I'm going to try -1, -2, and -4. So this is why I write this in this table form. That way I can keep all of my guesses in line without having to rewrite it. And then the first number always drops down. So we always multiply and add. So -1 times 3 is 3. 3 minus 11 is -8. Then I have -1 times -8, which is 8. 8 plus 8 is 16. -1 times 16 is -16. -16 plus 4 is -12. Okay, so that is not a zero because I did not get 0 in the very last spot. So, okay, got that down, not a 0. Now this is also, notice that I alternate signs here. I have 3, -8, 16, -12. So this is actually, if we go back to the upper and lower bound rules, if C is less than 0, so this is number 2, so I use -1, and the numbers in the last row are alternately positive and negative, so that's what we just had, then C is a lower bound. So what that means, if I go back, is since I tried a negative and these alternating signs, then I don't have a 0 smaller than -1. So I don't want to try -2 and -4. I can rule those out. So that means now I need to start trying the fractions because, and as long as the fractions are larger than -1. So if I go back, I could try -1/3 and -2/3, but not -4/3 because that one's smaller than 1. So now let's try -1/3 here. And I'm going to take a calculator because once you start with fractions, it's just a lot easier to do it on your calculator. So -1/3 times 3 is -1. -1 minus 11 is -12. -1/3 times -12, actually this works out nicely. That's not going to come out as a fraction, that's going to come out as 4. 4 plus 8 is 12. -1/3 times 12 is -4. -4 plus 4 is 0. So now I have found a 0. So I used the lower bound rule, I used the rational zero test, and I used Descartes' rule signs that said I had to have a -0. So what I have so far is x, and then if I had x minus If negative 1/3 is one of them, then I could write this as x plus 1/3 as our factor. So it's always the opposite sign. And then I'm left with a, let's see, I started with a cubic because I already factored out an x. So now I'm left with something that's 3x squared minus 12x plus 12. And now I have something that I can factor. Because I have a quadratic, I can factor or use the quadratic formula. And actually, when I'm looking at this, I see that I can factor 3 out of that whole quadratic. So I can write this as 3x. I'm going to just put the 3 in front. And then that gives me x squared minus 4x plus 4. So I just factored out a 3 from the quadratic and just stuck it in the front, just like when you factor out the greatest common factor. And now x squared minus 4x plus 4, that actually factors. So that factors nicely. That is x minus 2 times x minus 2. So now I have just factored this polynomial. So I used all of the information that they gave us to kind of narrow down my choices, and I didn't have to do that much guessing. And then I was able to factor the whole thing. So before I move on, are there questions here?
No, ma'am.
So now that I've factored, what comes next is pretty easy. It says list the zeros of the polynomial and their multiplicity. So we have factored this. We have 3x, we had x minus 1/3, and then x minus 2, x minus 2. So you set each of these equal to 0. So 3x equals 0 means that x equals 0. So that's a 0. Then we had x minus 1/3 equals 0. We know that one of the zeros is 1/3. Wait, that should have been x plus, right? Yes, I copied that wrong. So yeah, so that should be, we had one of our zeros was a negative, x equals negative 1/3. And then we have x minus 2 equals 0, which solves to x equals 2. And because that one shows up twice, that has multiplicity 2. Because it's listed twice. So we started with something that was x to the 4th. We ended up with 4 zeros, but one of them is repeated. So that's multiplicity 2. So now we've got all of the zeros and multiplicity. If I don't list the multiplicity, it's assumed it's multiplicity 1, basically. And then for sketching a graph, you can use perfectly, I'm perfectly happy if you just put this in Desmos and graph it, but just rough sketch. So we know that it has to look like, because from our end behavior, it's got to look like a polynomial on the ends. And so it's going to go down and through 0. And multiplicity means it bounces at that point. So it's going to look something like that when I sketch it. But you can use Desmos to get the picture and then just put that in your assignment. So that is basically how you do problem 1 on the assignment, just with a different example. So are there any questions?
No, ma'am.
All right. So that was all I had. I know this was a very long one, but there was a lot of definitions, and it's a lot to go over. But I wanted to make sure that I walked through a whole example of the assignment. So hopefully this is helpful. And if there are parts you're still confused on, of course, I can look for more examples. You can email me and find some more examples on YouTube or something to help out with that.
Okay, thank you.
You're welcome. So hopefully I'm going to try to post this soon. But yeah, hopefully this was helpful. And when is my next one scheduled? Go to my calendar. Oops. Okay, so the next one is going to be our introduction to week 6 at 7 o'clock on Wednesday. So that will be that. All right. Well, hopefully I will see you then.
Have a good day.
You too. Bye.